show up. We already got a pretty full room here. I'm Pepper Hastings with Innovative IDM, and welcome to our 40-minute webinar this morning, DC to AC drive retrofits. We're really happy to have you guys and are glad you took the time to invest in yourself and learn about DC to AC drive retrofits. Our presenter today is Steve Lyons. He's a proud former Cougar from the University of Houston. The great thing about Steve is probably when he goes to parties or work or social gatherings, he probably talks about AC drives. And so he's the guy to be leading this conversation for sure. And so I'm going to welcome Steve as our host. And Steve, go ahead and take it away, sir.
Well, good morning, everybody. Glad to have you come on board here. Our job today is to look at the value of going to from DC to AC. So I'm going to give you some examples today of what kinds of DC applications there are out there. We're going to talk about the DC versus AC performance and what it looks like in the cost of ownership of these systems. So that kind of an overview here of where we're going with this is the cost of ownership. And this is going to be the first slide here, and it's also going to be the last slide. So in between, I'm going to define what these actually mean. So kind of a history here of DC. It was started, I guess it was being pioneered in the very early 1800s and became a thing in the late 1800s, and industry was depending more and more on it. There were a number of industries that were playing in this game. Westinghouse, GE, and Reliance were kind of the big three in this system. At that time, you had a DC system looked like, it was called an MG set, and it was an AC motor driving a DC generator, driving a DC motor, and they got their variable speed out of the communications between the DC generator and the DC motor. So an application, there's a lot of them out there. This particular picture that you have here is a roll form machine. And it actually started out as an MG set. We eventually put a DC drive on it, and someday they'll want to update it to an AC, but right now it's running off of DC. It belongs in the Smithsonian, and it was a 1927 vintage. Anyway, there are other things. There's steel mills. Saw one out in El Paso that has all of the Frankenstein equipment still in it, talking to them about converting the whole thing over to AC. There's conveying systems, there's forming lines, there's various types of metals applications. There's plastics as well. Plastics extrusion is a huge part of, there's a huge following in DC still in plastics. From lab extruders, fibers lines, film lines, blown film lines, molded parts, and pipe and tubing mills, various types of extrusion that's out there that is now running with DC. Much of it has been converted to AC, however. All new equipment will be AC in all of these types. Aluminum extrusion, I ran across one over in College Station a few years ago. In the steel, again, there's this particular line is local in Houston, and it is forming a siding for metal buildings. But there's tubing mills. There's tubing mills all over this town and around the United States. Winding, conveyor systems, all of these things still have a lot of DC out there. So why would we consider a DC to AC retrofit? Well, the bottom line is you can't afford not to unless, of course, you've got money to burn. And that's the bottom line here, is the amount of cost of running a DC versus an AC system. So we're going to talk about that. But first of all, let me give you a couple of definitions so that you understand when people talk about the various types of drive systems, these are their names. And DC and AC share a lot of the same name: motor drives and variable speed drives and adjustable speed drives. And the DC drive is unique, obviously, to DC. Variable frequency is the definition of the AC drive. You also have, people will call them freak drives for AC, or they'll call them SCR drives for DC. So those are just kind of the names that are out there. But let's go to some of the pros and cons of why DC or why the AC systems. So AC systems and DC systems can come in single phase or three phase. The single phase are typically 120 or 230, 240 volt type. There are some 120 volt AC systems as well. They're three phase, 240 volt, 480 volt, 600 volt. Those are going to be your typical voltages in the North American continent. And with DC, there are a whole lot fewer components, so there's less parts to fail. With AC, it is considerably more complex, but it does have a longer life expectancy for their components. And it would seem that with AC and DC systems, the fewer components would be in the favor of a DC system. However, you have to consider that the life expectancy of the components in AC far outweigh the less complex DC systems. So in this case, it actually turns out that AC drives are more reliable, in the whole AC system is more reliable than the DC. And the reason for that, we'll find in a little bit, has to do with the DC motor. There's a few other reasons, but by and large, it is the DC motor. So in DC, you have some very interesting, well, there's just a comparison here. The efficiencies are affected by the DC drive has one bridge, so those are one set of losses. An AC drive has two bridges, so that's two sets of losses. And there's a small amount in the capacitor bank here. So in the efficiency side of things for the DC drive, it wins hands down almost 2-to-1. The both use a contactor of some kind. The DC is required. AC is for isolation, for safety, and some other reasons. The DC drive uses a line reactor on the AC side of it, and it's typically going to be about a 5% impedance. You're looking at trying to reduce the harmonic content from the DC drive, which can be quite difficult to deal with. AC does not require as much, and it's typically a 3% that is recommended. With a DC, sometimes you'll have, if you've got an old MG set motor, then you're going to need to put a DC reactor in that thing. Whereas AC, the DC reactor is in lieu of this AC input line reactor. So it's one or the other. And some of the larger drives of most manufacturers incorporate this. The smaller drives you need to add here. So the rest of the components in the system are pretty much equal, and when it comes to efficiencies of those type of systems. Now, as I mentioned up here, is the reason for these reactors is controlling harmonics. And so let's take a quick look at the harmonics in a system. Both types of drives use 6 input components, whether they're SCRs or diodes. Typically, an AC drive is going to have diodes, so there are some that have SCRs. But there are 6 of them, and they come in, 6 pulses are drawn off of the 3 phases. And the individual amplitudes of those harmonic pulses are approximately the same for AC and DC. You can get 12 pulse DC, but it's pretty complex and it's not practical to go much beyond that. Whereas AC, you can get a 12 or 18, you can even go higher, but again, it becomes increasingly impractical to do so. Possible, but impractical. So what does that look like? Well, with a 6 pulse type signature, you're going to get this double pulse positive and double pulse negative on your current. This is a current waveform from the looks of it, this is from an AC system. The DC system would have one more little piece right here and right here, but the signature here still looks the same. You've got so much energy in all of these higher frequencies. If you went to a 12 pulse system, it would look like this for your current and this for your harmonics. And so kind of you can see the efficiency gain just in the current waveform is much easier on your total system. So if you were to use a 12 pulse system, then you would end up saving a significant amount in the losses in your power distribution system. And the utility would also be happier with you. Well, DC drives in general are direct torque devices, whereas AC is an indirect torque device. DC, the current is torque. AC, you have to develop the torque by controlling the slip of the motor. The DC drive is an indirect speed control. You use torque to achieve speed. The AC drive is a direct speed control, and you use the speed and the slip in order to control torque. Both of them use a field weakened method in order to go beyond the nameplate base speed of your motor. DC does have, by the way, a regeneration capability if you add a larger model that is a 6 forward, 6 reverse SCRs, whereas AC is naturally regenerative. It's just the way it is. You can go forward and reverse with it, everything, but you do have to do something with that regen energy with AC. And whether you're dumping it onto a resistor, you're sharing it among multiple drives, or you're dumping it back to utility, you've got to do something on the AC side with the regenerative energy. And so it does require additional parts. Reversing, again, is natural, but reversing with the DC drive, you can do it with a regen system, or you can do it with addition of output contactor arrangement. So a summary, the DC drive converts AC to DC for a motor. The drive is inherently more efficient, but it's less reliable, and it's less reliable because of the motor. You get 6 pulse type harmonics. It has direct torque control and indirect speed control, and it can be field weakened and can easily regen, but you have to have the regen model. Where the AC side, it again converts AC to DC, then back to AC. That's why it is less efficient, because there's 2 conversions, yet it is more reliable. 6 pulse harmonics, you can get a 12 pulse system pretty readily. 18 pulse, even more are available, but 12 and 18 are pretty common. It indirectly controls torque and directly controls speed. So each one of these, it seems as if the majority of the positives fall into the DC side of things as opposed to AC. And indeed, it seems to on the surface. So why not just keep DC? Why would we go to AC? Well, let's consider that and let's talk about the motor. The motor is a big part of the reason for this conversion that we're talking about. With a DC motor, your rotational speed is limited on the low end by the ability to cool it and by commutation. If you go too slow, you're going to have problems down here being able to cool the commutator, and the commutator getting hot will cause damage to the motor. At the top end, you'll run into commutation problems as well. Typically, you're going to get any DC motor you have, you can naturally run it probably down to 1/10 of whatever your base speed. There are some models that will allow you to go down to 40. It is not recommended that you put DC down at 0. The current into the commutator bars will raise those bars and do mechanical damage with a hot spot. Whereas AC, it is also speed limited depending on its thermal design. Most cases, an AC motor can run to half speed and still thermally cool itself. Many of them are able to run down to 1/4 speed, and inverter rated motors are typically run down to 10 or 20 1/10 or 1/20th of your rated speed. If you go into vector duty, you can get into the 100 or 1,000 to 1 range. 1,000 to 1, you're effectively at 0 speed, and you can continuously put 100% torque out of that motor at 0 speed with AC. So in that, these are about equivalent. However, the speed range of the AC motor is much broader than that of DC. By the way, I didn't put a slide here on it, but the DC motor is actually better when it comes to above base speed. If you start getting into 4 to 1, 5 to 1, or 10 to 1, the biggest I've actually ever seen was 8 to 1 of whatever your base speed is. It becomes harder and harder to do that with AC, although there are some winding designs that will allow it. So let's look at the DC motor versus the AC motor. The DC motor has a commutator which will wear, and it has brushes which will wear. And there's commutation, the commutator failure due to wear. That's the primary failure point of a DC motor, is this commutator. That is it. If we could eliminate that commutator, the DC system would be quite robust. But as you know, you cannot eliminate the commutator because that's the magic of DC. The field winding does have failures. Most of that is from loss of cooling. There's bearing wear, and there's other kinds of catastrophic failures that can occur. But the DC motor is the primary reason for DC drive failures. On the AC side, you can have stator and rotor failures. Rotor failures are very uncommon. Stator failures are I'm not going to say they're common, but they're certainly less common than problems you have with DC. And again, you have bearing wear. You get about 6,000 hours of natural life out of a bearing. So you have to deal with that no matter what you're doing. And in terms of the maintenance, the brush maintenance and the commutator maintenance is the big deal with DC. If you don't keep that up, you're going to have failures. You still have to have the same greasing mechanisms or regiments for both AC and DC. But with AC, there is no rotor or stator maintenance that is required. It either works or it has failed, and they're much more robust because they do not have brushes or a commutator. So kind of in summary here, the DC has this commutator system, which is its primary failure point, and so the AC wins out in its failures. They're much fewer. The DC system does require a significant amount of PM effort, whereas it's very simple, just maintaining the grease on the AC motor. And if you've got a belted system, you have to maintain the tension of those belts. The AC motor can go all the way down to 0 speed if it's designed to do so and cool itself just fine. The DC cannot do that. You'll damage the commutator. So the primary cause of drive failures between these two is the DC motor failure. ACs typically don't fail. And even if you have a motor failure, AC drives, modern AC drives, can typically protect themselves from that. So again, why not DC or why AC? And it's all about the downtime risk, and so far what we have covered here. But let's also take a look at the efficiencies of the system. So with a DC system, you have efficiencies, well, both sides. You have drive, you have power factor consider, you have the motor, you have the rest of your system losses giving you a total system efficiency. Well, with DC, again, the drive is far more, well, it is more efficient than the AC side of things. You're not going to get 99% efficiency on the AC side in today's technology. But 97 to 98, 98 and a half, those are doable. So there's not a lot of spread that you have between these two sides. However, DC does win. But the power factor of your system definitely suffers with DC. DC, the power factor is proportional to speed. AC, the power factor is virtually unity. But then we have to consider the motor. If you look at this chart, you have AC motors here in blue and a range of DC motors that I have from one manufacturer. Their efficiencies range from somewhere around 0.81 all the way up to 0.83 0.84. And for 25 horse, by the time you get to 500 horse, it's pretty much about 93% efficient. And everywhere in between, but it's all the way across the board is less than AC. EPAC has required AC efficiencies go up. So if you look at that, the motor efficiencies, and I've been very generous here to DC, is somewhere between 88 and 93%. And the motor efficiencies required by EPAC are between 93 and 96%. That is a big deal that these efficiencies are high. These two over here are the downfall of your DC system. And that's what ends up contributing to the losses in DC versus the losses in AC. It is the power factor through your power distribution system, low power factor. For the same amount of work, you've got a lot of current. For the same amount of work on AC, you have proportional to speed is the current. Here, the current is directly proportional to torque. Here, it's proportional to speed. So with the motor being low efficient, the motor over here being high efficient lends to a very efficient system. So when you're looking at the DC, we also have to consider the repair side of it. With DC systems and their reliability, you end up with something in the order of 3 to 5 years mean time between failures most of those failures are the motor side. With AC, you end up with a mean time between failures between 12 and 28 years. And we have several customers who are realizing these kinds of reliabilities. So the average cost, and this is kind of about a 40 horsepower example here. The cost of doing a repair, your field service guy is going to go out there and he's going to find out what's going on. Let's say it takes him a day to do so. And the repair shop, if they're going to repair the drive, you're going to be actually, because it's simpler, DC is a little bit easier to repair than AC, so the costs are reflected here. But the motor shop is going to be your biggest deal. Those motor shops are not cheap in motor repairs. You can get an AC motor redone very easily compared to a DC motor. And so if you consider these costs of approximately $21,000 per repair for a DC system, or $13,000 per repair for an AC system, times the number of failures, you end up with a significant cost savings over the life in AC. So an individual, the AC is going to win in all of these categories. Well, it's easier to repair a DC motor. I mean, a DC drive. So the savings on a single event between DC and AC is somewhere in this side of the pie chart. And then over the life of it, times the 6.7 failures in DC versus about 1.7 failures in AC over a 20-year life, DC is going to give you a lot of downtime, a lot of repair costs, and overall repairs are going to be running around 140K versus about 20K. That is 21,000 times 6.7 versus 13,000 times 2. So when you deal with this, the DC costs to downtime, the DC cost of repairs, and the DC cost of efficiency. Here's an example again of a 40 horsepower power consumption based on the efficiencies. You're roughly going to have 280 kilowatts versus 260 kilowatts. So that 20 kilowatt difference is a savings in just the efficiency of the system. If you take that and apply it with your downtime, I guess I got these slides out of order. I had not noticed that. Your production loss time is about the same between DC and AC systems, assuming a 4 hours to 72 hour downtime. It's going to cost you an estimated $1,000 an hour of lost production. Purely a simple example. Some people are in the order of hundreds of thousands of dollars per hour. Some of them are less than 1,000, but let's just call it 1,000. And so you're going to have a lost production of somewhere between $4,000 and $72,000 per event, times the number of events, and that's where this was out of order. So the cost of production loss, you have the cost of production loss of DC versus the cost of production loss of AC. You have the cost of repairs for DC, the cost of repairs for AC, and you sum that all together with the watt losses of your system, and you end up with a total life cost of AC being significantly lower cost of ownership than DC. Now, I do admit that not included in here is the cost of a DC system versus the cost of an AC system. These numbers would be even greater because the hardware costs of DC are now greater than the hardware costs of AC when it comes to a total system thing. Well, when you can take all of this into account and the loss of production, the loss of utility, and the costs to maintain, you end up with, and I'm very generous on this, DC costing you between 20 and 70% more than AC. So the question comes, how can you not afford to do a DC to AC retrofit? And I wanted to add one small thing that I did not put on a slide, but I want you to consider that we have the ability to come to your site, run measurements on your existing system, project all of these categories of losses for you, and when it's all said and done, we can give you an estimate which will include the cost of new hardware, installation costs, etc., versus what it's costing you to operate your DC today, and show you the projected payback on going from DC to AC. So just let your sales guy know that you might be interested in that, and we can do that for you. Well, that's what I have to present today. I'm a little bit ahead of where I expected to be. So with that, any questions?
Thank you, Steve. I had a couple of people PM me. I had Donovan. He said, how much downtime does a typical DC to AC retrofit take? I don't know if that's, you can answer that or not. Maybe different with all.
Well, it depends on the size of the system. Small systems are obviously going to be faster than larger systems, but say a typical 100 horsepower, if you do everything linearly, you'll be down for about a week. If you can do the drive retrofit and the motor retrofit in parallel, you would be considerably less, maybe 2 to 3 days. But I would still schedule a week just in case.
Okay, we had another one in the chat window from Roman. It says, what is the cost of the conversion for 600 horsepower DC motor to AC? 600 horsepower DC to AC.
Look at that specifically, because one of the things I've never been able to do is keep those kind of prices in the forefront of my mind.
Well, is it a dollar or a million? I mean, what?
Well, I can put it two different ways. It's less than $1 million, or I can say it's $1,298 plus accessories.
Okay.
Now the 600 horse motor, we just did a smaller AC to a larger AC. We actually shipped out the equipment yesterday, and I was trying to remember the ballpark of that. The motor is the larger cost. That it's going to be larger than the drive, but it also depends on what you're dealing with. Consider, are you dealing with atmosphere that has corrosives in it? We're going to have to deal with that in the cooling processes on both your VFD and your motor. If you've got contaminants, you have to deal with that in the cooling systems. So it varies depending on what your application is, but that is something that we can do a very accurate estimate on if we come and look at it.
Okay, I had David that asked, can you give an example of any retrofits you're doing right now, or I guess recently?
Well, we have one on an extrusion system. It's a pelletizing system. And they wanted to up the size. We actually did not go from DC to AC. We went from AC to AC, but effectively it's the same thing. The customer wanted to have, instead of his 500 horse, he wanted to get up to 750 horse on his system. And they're in the process right now of doing that. It's out actually just west of Houston. We in the past few months, we have done several between 200 and 400 horse DC to AC retrofits for plastics extrusion plants. I did a DC to DC retrofit on a steel plant where we updated the DC systems. It's not part of this presentation, but there is a demand out there to still maintain DC for their big stuff. And we can do that as well. We can refresh or refurb your existing DC. And if your power bridge on large systems is in good shape, we can put a new control system on top of that.
So I got
things we can do here.
Okay. So another question here from Matthew. For torque critical applications such as extrusion, what is the best way to indirectly control the torque?
That is easy. It is a vector control. You will end up with equal to or better than DC performance when you go with a flux vector type AC drive. The math model actually directly watches the slip of the motor, which is torque, and adjusts accordingly to control that torque. Motor slip is torque with AC. Just like with DC, current is torque.
Okay, thank you. Here's a question from Clint. Can you talk about the difference in brushless DC versus permanent magnet AC, specifically for higher performance position control?
Okay, so the history, we used to actually represent the brushless DC market. The guy that did that, he sold the DC drive systems to Emerson Industrial Controls. And for years, you may even have a history of knowing the VIP drive, the Spectrum drive, and so on. He had developed all of that. Well, he left that company and started his own, and it was originally called WearTech, and they had a lawsuit, and he had to change it to PowerTech. And this guy developed the brushless DC. So let me give you, he called it that for marketing reasons. It is actually a permanent magnet AC. That is, the brushless DC is permanent magnet AC. And there are various forms of permanent magnet AC out there. Permanent magnet AC is a design that you no longer have slip in the motor. The motor follows the frequency of the AC drive, and so it is a highly regulated speed system because the shaft of the motor will follow whatever the drive tells it to do. So brushless DC and permanent magnet AC, the winding system's a little bit different. The way that it is driven is a little bit different, but in the big scheme of things, it's the same animal, and calling it brushless DC is a marketing thing. It's a misnomer because it's actually AC.
And so Clint was asking about, a higher performance position control application. Is there anything you want to add to that?
Yes. So in terms of position control using the permanent magnet, again, the speed will sync lock with the rotor, making it much simpler to position the shaft, because you are literally positioning the shaft with every, as your three phases chase around the circle, you are with a synchronous system where the AC motor, the permanent magnet AC motor, is going to be synchronous with whatever the drive is putting out. So you can much more easily control the position loop with the encoder feedback where you're sync locking two or more motors. Does that answer the question?
Thank you. Yes, Clint says yes, thank you. And there's no more questions. I'll give you another few seconds here to type anything in to the chat box. But Steve, we want to thank you for your time today, taking time out of your day to talk about something that you can tell you're very passionate about. And I want to thank everybody that showed up on the webinar to thank you for investing in yourself.